Hello, my name is Jack Bohr, and I'm here to present my team's paper, From Chaos to Calibration, a geometric mutual information approach to target-free camera-LiDAR extrinsic calibration. Camera-LiDAR extrinsic calibration is used to fuse camera and LiDAR data into a common spatial reference frame, which is often required by sensor fusion perception functions in robotics or autonomous driving systems. On the left side, we see the projection of the LiDAR onto the camera image using the incorrect value of the extrinsic calibration. And on the right side, after our proposed calibration process, the projection of the LiDAR onto the camera using the correct extrinsic calibration. There are many existing target-based camera-LiDAR extrinsic calibration which use checkerboard targets or other 3D targets to provide common, correspondent, easily identifiable geometric features in both camera and LiDAR sensors. However, these are labor and time intensive, often demand a technical expertise, and requires an engineered environment which prohibits their use for online applications for robots or vehicles that operate in the real world. Target-free camera-LiDAR extrinsic calibration, on the other hand, uses only sensor data, in this case, camera images and LiDAR point clouds. They're automatic and labor-free, require no human expert, and function in common natural real-world environments. One of the most prominent target-free camera-LiDAR calibration approaches is mutual information-based calibration, which says that the mutual information of a feature in the camera and a feature in the LiDAR will be maximized at the correct value of the extrinsic calibration. And up to this point, the most common used feature has been image intensity and LiDAR intensity. And as we see in the image on the bottom, when they are projected at the correct value of the extrinsic calibration, they do share features. If we look more closely, we see, for example, that traffic cones have a high intensity response and also have a different intensity in the image space. However, we see that the correlation is not exact and depends on the presence of highly reflective objects, which cannot be guaranteed. Our approach uses self-supervised monocular depth estimation networks, which have been popularized starting in 2017 to transform the camera into a pseudo-depth sensor. This pseudo-depth sensor is then highly correlated to the LiDAR, which is a real depth sensor. We then calculate what we call the geometric mutual information in between the image, which has been transformed into a depth map, and the LiDAR point cloud. And as you see in the graphic on the bottom of the projection of the point cloud onto the image, these two are highly correlated and share mutual information. Our entire method is summarized here. We turn the image into a depth sensor with monodepth network. We project the point cloud onto the image, and then we maximize the mutual information between the two features, in this case, two geometric features. And then at the end, we get the extrinsic calibration, which allows for the correct projection. Here, we see a comparison of the mutual information surface around the correct value of the ground truth extrinsic calibration for intensity on the top and geometric mutual information on the bottom around the three rotation axes. And as you see, the geometric mutual information is much more well-shaped and easy to optimize from a larger initial error. And here, we compare the convergence of different optimization runs around the value of the ground truth extrinsic calibration in what we call a bullseye plot for the intensity mutual information on the left and the geometric mutual information on the right. And what's immediately apparent is that geometric mutual information on the right is much more precise and very accurate compared to intensity-based methods, which often fail even at small errors. And yeah, please feel free to reach out to us first, last at spleen.ai. Thanks.